As the service has grown and matured over the past 15 years, the software has evolved a lot, but so has the organization and the way that we think about durability. At reInvent in 2019, Seth and I gave a talk about how we think about durability broadly in S3. And we used the idea of a durability threat model as a way of thinking through durability risks in systems. So we considered risks not just from hardware failure, but all sorts of other stuff like operational events, physical disasters, and several other things. To build on that talk, we wanted to talk to you today about how a huge aspect of durability at S3 scale is actually the engineering culture and training the engineering team to be great at writing code and designing systems that safeguard customer data. One specific mechanism that we have for this is the durability review. The durability review is a meeting where we sit down as a small group and we look carefully at the potential durability impact that a change might have. As a mechanism, it's really effective. And it's something that we think has application outside of S3, even outside of durability. It's a useful way to review sensitive changes to any kind of system. So after the reInvent talk in 2019, we heard from customers who wanted to do durability reviews as part of their own development. When a customer does a durability review, they're testing the durability model for their own application code. While the storage is in S3, the data is protected by the durability design of S3. The threat to durability that many of our customers worry about and are interested in reviewing is the code that lives above S3, that gets data from S3, transforms or analyzes it in some way, and then stores the data back into S3 again. So today, we're going to walk through how the review works in a bit more detail and work through a concrete example. So regardless if it's S3 or a customer's application, the team that owns a change that's being made is responsible for holding the durability review. The review starts with a written document. Writing down the threat model is really important because when you sit down and explain it in a written document, it forces you to kind of look at your system slowly and deliberately and to get really clear on the thinking that you might not otherwise get to. So the document that's produced for a durability review acts like a map, right? It's really intended to guide the discussion in the review and to help reviewers focus on questions. We typically book about 2 hours for a review, and when everyone meets up, we spend the first 30 minutes quietly reading the doc. The tone of a review is intentionally constructive, not really stressful or critical. We're all there together to try and find issues and to really focus on improving the software that we're looking at. Typically, we try to structure things so that the most senior folks in the room talk last, so that we can give everybody an opportunity to ask questions and not feel like they're on the spot. Another really kind of critical aspect of these documents is they're tricky to write, right? They take a fair bit of time to get really good at articulating and to effectively guide discussion in. And it's a really natural thing when you're initially writing a durability doc for review to make it really, really comprehensive and sort of necessarily complex. And what we find as folks get more experienced writing these documents and running reviews is we really work to get the documents to be as compact and simple as possible. So even if the code itself that the review is covering is complex, it's important to be able to think about durability really simply. An example for that we'll talk about later in the talk is the idea of guardrails. That even for really, really subtle parallel systems that are doing a lot of things, it's often the case that we can build mechanisms in terms of how we protect data and integrity and durability that are relatively simple end-to-end strategies that even if subtle things go wrong are going to be caught by these sort of coarse-grained mechanisms. There are two major parts to a durability review doc. The first one is to describe the threat that you're worried about. This is the threat model, right? The goal of the threat model is to step back and think in really broad categories about the types of things that might go wrong. And after the threat model is articulated, and it's usually like a really short, compact statement, often a single paragraph, the rest of the doc uses the threat model as a lens to call out the risks and the countermeasures that fall out of the change as viewed through that threat model. The split's really important because it allows reviewers to have two separate conversations in the room. One is to poke holes at the threat, the description of what might go wrong, and doing that without thinking about the change or about thinking about the details of the code in the system mean that you can step back and just think really broadly, possibly identifying new threats or risks that haven't been considered. And then separately, once everyone has that threat model established, they can use it to review the change with that threat as a basis for considering it. Separating these conversations up front lets everyone in the room agree on what the precise threats are that you're reviewing, and then use those threats as a lens to evaluate the change that the document's describing.
Thanks, Andy. So like Andy described, we're going to use an example to talk about the key concepts of writing a durability review. So in this example, let's take a fictional company with petabytes of data stored somewhere. They just invented a new deep learning-based compression algorithm and want to compress their entire data set. And so the idea is that new data will be compressed with this scheme and that they want to backfill existing data to this scheme. And so let's say they're holding a durability review for this particular change, and Andy and I are two of the reviewers there. The engineers writing this compression system want to hold a durability review, and so let's talk through how that might go. As you're first approaching these as a presenter, the common inclination is to just write up a big list of specific things that could go wrong. But that ends up being really hard, and it's really hard to know if you've gotten everything. And so there's a better way to organize your thinking here than to just make a big flat list of things that can go wrong. Basically, you want to think about the problem in terms of a tree structure. At the root of this tree are your threats. This is what Andy and I talked about at our reInvent talk in 2019. So threats are a high-level statement about what could go wrong. There's a bit of art to writing threats because you want them to be high-level enough, but not uselessly vague. And so what you're really trying to do is to be just high level enough to categorize specific risks that you're about to list. So back to our example here. Let's say the presenter comes with what they think is their only threat. And I'm going to kind of read what, their threat, how their threat might be articulated. We are going to deploy a new compression tool on the write path that will transform all new data. We're also going to include a decompression tool on the read path that will need to be able to decompress that data at any future time. Our primary threat is that we don't trust the code to be perfect. It receives both data and metadata, and it may cause problems as data is transformed and make that data unreadable. Okay, so that's a threat, and that's actually really well written. It's high level enough in that it doesn't really mention how things could break, but it does address what could happen and kind of addresses the so what of what the threat is. So it provides a pretty good framing for expanding into specific risks, which we'll get into next. But before we get into specific risks, what often happens in these durability reviews is that we spend a bunch of time discussing these threats to see if they're the right ones. It's important that we capture all the threats, otherwise we'll miss like these huge swaths of specific risks. Threats are a fairly easy thing to brainstorm on, even without having a deep understanding of how the system works. In fact, folks in the audience here might actually be able to think of more threats just from this fictional example. Anyway, in this particular case, there's at least one more threat that we could bring up in the review. And so I'm going to read what that threat could look like. The decompressor relies on an external model to be able to decode data. That model itself is a piece of data, and it's especially valuable to the system. Without it, all of the compressed data is rendered virtually unreadable. And so that model might change over time as we evolve this algorithm. And a problem in changing that model could destroy the model file and render the entire data set unreadable. And so that's a new threat that the team didn't come to the review with, but it's an absolutely legitimate threat. Now, in practice, there's probably more than just these two threats, but for the sake of time, let's say we brainstorm a bit and those are the only two threats we can identify. So we then want to expand the threats and get into specific risks. This is what I meant earlier by modeling the thinking here as a tree, right? We start with the root, which is the threat, and we're expanding it. So risks are very specific root causes for the threats that were identified. And so engineers will come to these reviews with a big table of risks, and they usually group the risks by threat just for readability. And so every threat would have a section of risks associated with it. And oftentimes, like you just saw here, when we have identified new threats in the meeting, we'll come up with risks for that threat right then and there. Right, the threat that I mentioned, the team that presents the review would probably think of 18 ways in which that could happen. But more often than not, the presenters also need to go off and think more deeply about newly identified threats. It doesn't all happen interactively in that room. So anyway, for the sake of for the threats that we just cited here, we might have a few specific risks. Again, this isn't going to be an exhaustive list because just for time's sake here. But here's some risks. So the compressor might have bugs that corrupt data in a way that can't be decoded. It's a risk. The compressor might accidentally change the name of the file it's processing and write out the resulting compressed data to the wrong place. Some portions of the compressed object might actually end up triggering edge cases and crash the decoder, rendering the object permanently unreadable. The compressor might say it's written a compressed file successfully when in fact it hasn't, but then it goes and deletes the source file. And so compression somehow is a no-op, but then it assumes it was correct and deletes the source. In updating the model, the old model file might be permanently overwritten. And when there are multiple model files, we might not be able to tell which to use to decompress a particular file. This is especially problematic when the number of model files grows really large, and so on. There's effectively a huge list here. And so each threat will have a bunch of these risks. There are some broad categories of risks that are useful to keep in mind as you think through this for your review. Those broad categories are some of the things that Andy and I talked about in our 2019 reInvent talk. They're facility failure, hardware failure, data corruption, both in transit and at rest, bugs, which can land both in the implementation and the design of your system, deployment issues, and operator error. And so sometimes thinking about those categories of risks help you think through what your risks might be for a given threat. So after thinking about these risks, we continue with the tree analogy and expand the risks to identify mitigations or countermeasures. The mitigations are things that prevent the threat that the risk poses. Risks could have multiple mitigations depending on what the risk is. And in the document, this table of risks that I talked about usually has a column in it that refers to their mitigations. And so we have the threats listed out, and then you have tables sort of per threat that list the risks that can cause that threat. And that table has some columns in it. The mitigations would be like one column. So let's just list out a few mitigations from the risks that we mentioned earlier. One way to mitigate that the compressor produces data that cannot be decompressed is to actually do decompression in line with the compression and validate the result before committing the compressed data. So this would be something that the compression code would have to do on every single file. One way to mitigate the risk of overwriting the model file with updates is to generate a GUID for each model file's file name so that we won't risk overwriting old models. So these are a couple example mitigations that we would implement in the code that would address those risks that were identified. Okay, so at this point, we've expanded the tree from threats to risks to mitigations. But we need to think about defense in depth in these reviews. And so engineers need to think about what they'll do when all of their mitigations fail. Because theoretically, like we have everything covered now, right? Like all the risks are mitigated, so the system should have no problem. But we're going to think about this kind of in layers, defense in depth. And so these things that we do when the mitigations fail are called guardrails or safeguards. And they're the things that protect you when all else fails. And it's important that we think about guardrails and mitigations separately. We don't want to get lazy with one of them, assuming the other will save us. So you don't want to shortchange your guardrails because we have mitigations for the issue, or not mitigate your problems because the guardrails will save us. Each of these categories have to be thought of independently and as if they're the only thing that's going to protect the system. And so in this fictional example, there's one guardrail that the team came up with. For each data file being compressed, instead of overwriting the source file, they're going to write the compressed data to another file and keep the original around for a while. This doesn't address any single risk directly, but it creates a safety net in case an unexpected problem is discovered that needs to be reversed later. The source file won't be kept forever in this case, because that would be costly, but there will be a few weeks of lag between creating the compressed data and removing the source to give time to learn about unexpected problems. And because the team in this example hadn't pre-considered the threat of the model changing over time, they hadn't come up with any guardrails for evolving the model itself. So we brainstormed this in the review. The model files themselves will be written to a version data store and replicated into a backup system that allows recovery of any previous model file. And in this case, the models themselves are small, and so we can simply just keep all the models forever. There's no reason to garbage collect these later. So at this point, excuse me, we have our tree of threats, risks, and mitigations. And then we also have guardrails that protect us in case those mitigations fail. But we're still not done because we still want to be paranoid here. So even though we have defense in depth, we have to be able to identify when something goes wrong. We have to make the system observable. And there's 3 ways that we do this. And most projects will use a combination of all 3. And so those 3 ways are metrics, canaries, and auditors. A metric is just a measurement of some dimension of the system. For example, in this fictional example, if the decompressor encounters a file it cannot decompress, we should emit a metric here that indicates a problem. And then operators can act on those metrics if it encounters them, or if the operator encounters them, and then root cause the issue. A canary is a separate application written that exercises your system and validates its results. In this case, the canary would send new data into the system, which would be compressed, then read that data back out to make sure it's still readable. The canary might also read data that it's written in the past to make sure that it's still readable. Canaries aren't perfect. They act like a customer to your system, but they're only one customer. You might have millions, and they won't cover all possible edge cases and workloads. But these canaries still do experience some of what your customers do, and so they add a lot of value. And lastly, in the list of ways that we make the system observable is that we look for auditors. And so an auditor is another application that can walk the system state and validate that data or behavior are both correct. So auditors need to be able to reason about what it sees to judge if it's correct or not. So in this case of the fictional compression algorithm, the auditor could constantly read back all files in the system, decompress them, and validate that they're correct. To do so, there needs to be some checksum or some other mechanism that the auditor has access to so it can assert its correctness. And sometimes auditors can exhaustively audit a system like we saw here, but other times it would be infeasible either because of cost or other scaling issues, in which case you might have to do some sort of sampling auditor that would choose a subset of your system to sample. The key with all of these observability techniques is that they're always running. So metrics are being produced by the live system, and the auditors and canaries are actual processes that are running constantly. None of these things rely on the good intentions of the operator to remember to run during a release cycle, and they'll all alarm the operator when an anomaly is observed. And so what we've covered here is protecting your system via coming up with your threats, expanding those to risks, and expanding those to mitigations, and then layering the protection or defense that we have by adding guardrails, and then measuring the system so that we can observe its actual behavior against what we think.
Thanks, Seth. All right, so what happens at the end of a review? The customer application team in this example doing the durability review would generally have appointed a note taker ahead of the meeting who focuses on writing down all the things that are raised during the 2 hours or so of the review. So after the meeting, the team will circle back and they'll go over those notes and they make a list of all the things that they learned. And then they decide what they're going to do to address any concerns that were raised that they hadn't thought of. It's really important that teams own their own durability and make these decisions. But there's one final important aspect of the review process to talk about here, and that's when should the review happen? And the answer to this is actually that it should happen as early as possible. In general, the best way to avoid a durability review becoming a gate that introduces big surprises and slows down development is to get the team to do it as soon as possible. And this is like a really important thing of the way that we look at these reviews. We never want them to be a sort of panel that blocks us from moving fast in terms of development, from being really, really like agile. We want them to be a mechanism that teams really feel that they're using themselves to hold a high bar for their own quality and their own durability. And so by meeting as early as possible, we can sort of bring forward any of those discoveries and react to them, as early in the development process as possible. Similarly, when a developer is writing the doc, we encourage them to do pre-reviews of drafts of the doc, often one-on-one with someone who's had more experience writing review docs or doing reviews, to make sure that they're getting the structure right and to test to make sure that the doc is focusing attention in the right places. The most important bit of all of this is that the durability review is really just a way to get useful information about the risks in software design. And so everything we've talked about it is around using it to focus attention on the right information. Think through countermeasures to protect a system and get the information that impacts design as early as possible. And so that's really it. That's the process that we use. And we find it really, really effective at holding the high bar that S3 holds for durability in all of our systems. And we hope it's useful to you as well. Thanks.
Thanks, everyone, and enjoy the rest of Pi Week.